All right, today we are on 1.7, three-dimensional figures. Okay, so our objectives are to identify and name spheres, cones, cylinders, polyhedral, including prisms and pyramids, and identify some terms related to these three-dimensional figures. So there's a lot that we're going to do with these three-dimensional figures that you've heard of, you've seen for years and years and years. We're just going to learn some new vocabulary about them. Okay, so first of all, the surface is a connected set of points in space having the thickness of a point. So just any surface, it's a connected set of points. Okay, a sphere is the set of all points in space that are a given distance from a point. Okay, like that's the center, the sphere's center, right? So then here I have these that come forward and go up and below and behind, just a sphere. Okay, so any segment from the center to a point, any segment from the center to a point on the sphere is a radius. Okay, so it doesn't matter if it goes from the center to the right or the center to the front here. I know it's going to look a different shape or a different length, but it's still a radius. It's just drawn with dimension to it. We're trying to put a three-dimensional shape onto a two-dimensional sheet of paper. Okay, so don't let that confuse you. All right, a circle, we already learned this, is a simple closed curve. Okay, it's also the boundary of a region, because remember, the circle is the boundary, the region is the circle, the boundary, and everything in it is called the region. A sphere is a closed surface. Okay, so it's the boundary of a solid. So the sphere is the closed surface and the interior. Cones and cylinders are also closed surfaces. Okay, so cones and cylinders are also closed surfaces. So a closed surface is just a surface of finite space that divides space into an interior and an exterior. So we have inside the sphere and exterior of the sphere. Inside the cone, outside the cone. Okay. A cone is the union of a region and all the segments that connect the boundary of the region with a specific non-coplanar point, the vertex. Okay, so the cone has a vertex. That's what we want to remember. So this right here, it has a vertex, so this is considered a cone. Okay, it's a really odd shaped cone, but it's a cone nonetheless. And it's a closed surface because it has finite space, okay, that divides it into an interior and an exterior. So some of these definitions seem like really far out there, but they're just trying to help you understand that a cone, like sometimes a cone is more than what we think of, like, you know, when you think of the waffle cone or whatever shape. If it has a vertex to it, okay, and it comes off of a flat surface, then goes to a vertex, then it's a cone. A cylinder then is the union of two regions of the same size and shape, same size and shape, in different parallel planes. So they're also in parallel planes. And the set of segments that connect corresponding points on the boundaries of the regions. So here, these are prisms, okay, because they have two regions. It's a union of two regions down here and up here that are parallel planes. Maybe I should have outlined it. That just makes it look a little more complex, I feel like. So let me go back. So right, it has on the bottom, it's got like this shape here. On the top, it has that same shape. So there's two of them and they're parallel to each other. Here, that shape is a pentagon on the top and the bottom. Okay, so it's two pentagons and they're bound together. Okay, but those pentagons are parallel to each other. So that is a cylinder. Okay, I'm going to clean this up and we're going to move down. Okay, so a cylinder or a cone is circular. A cylinder or a cone is circular if each base is a circular region. Okay, so it's circular if each base is circular. Fair enough. So if we look here at this circular cone, right, the base is circular, so it's a circular cone. Here at the cylinder, the base is circular, and this base here, right, would also be circular. So we have circular bases. It's a circular cylinder. All right. A cone with a polygonal region, okay, polygonal region as its base is a pyramid. Okay, so here our base, notice, looks like a rectangle. It might look like a square, but if it was a square, and it says it's classified as a square pyramid, but we would like to see some marks on there that it shows that each side is equal. But that's a pyramid because it has a polygonal region for the base. Okay. Then, okay, a cylinder, okay, a cylinder with polygonal regions as bases, right? So there's two of them, is a prism. So this is it. We look for the part that has two of the same shape. The base is not always what's sitting on the floor. Okay, a lot of times we think of like, or maybe what's on the bottom. It's not. We have two triangles and they're connected by three rectangles. So the part that has two, okay, is the base. Okay, so this is a triangular prism because the base is a triangle. This is a square pyramid because the base is a square. Then we also have right polygons. Okay, it is when the lateral surfaces are perpendicular to the bases. Okay, so what that means is, so remember the base is this circle down here, right, and the circle at the top. And so we want the lateral surfaces. So this is the lateral surface. All right, so those lateral surfaces are perpendicular to the base. So if I drew a line down here, they would be perpendicular to this base. Or we could say if the vertex is centered above the base is another way to look at it. Okay, this one is oblique because it is not a 90 degree. This lateral surface is not 90 degrees to that base. Okay, or this lateral surface here even. However you look at it. Sometimes I draw it in the center, but it's not. Okay, like if I were to draw this one here, this down here, like from there to there is, but this is not 90, right? That's not 90. So it's not perpendicular. It would be oblique. Okay, let me clear this up. All right, some more definitions here. So we have a lateral face, okay, of a 3D figure is defined as a face that is on its side. So a face that is on its side instead of on its top or bottom. Okay, so if we look at this, so we have this triangle, right? But this is the base. So you notice the front and the back are both triangles. All three other sides are the lateral face. Okay, because it's the face that is on the side. So that whole thing here, this rectangle, is a lateral face. Then we also have a lateral edge. Okay, the lateral edge is the segment formed by the intersection of two lateral faces. So we would have a lateral edge down here, and we would have a lateral edge up here, and we would have one back here where you can't see it. Okay, because it's going to connect this lateral face on this side over here, right? There's going to be a lateral face there to the base. So lateral edges, segment formed by the intersection of two, let's make sure we understand this, of two lateral faces is called a lateral edge. Okay. So let's look at example 1. It says use the right square pyramid. So notice they're telling you that it's square. That means that you know each of these sides on the bottom is congruent. So use the right square pyramid to name the following. Okay, you also, by it saying it's a right pyramid, you know that this vertex, right, is perpendicular to the base. All right, but anyway, let's name its vertex. Where is the vertex? Okay, fantastic. The vertex is point D. So we would say point D is our vertex. B, its base. All right, remember they told us it was a square. So we're going to write square. And then to name it, we just pick a place and go clockwise or counterclockwise. So I'm going to start at L, and I'm going to name it L, M, N, O. I'm going counterclockwise, L, M, N, O. But I named it in order. Lateral faces. Where are my lateral faces? Okay, notice, so my triangle or my square is the base, so I have a lateral face right here, which is what shape? Good, it's a triangle. So this one is M, N, D is what I would call that lateral face. So triangle, M, N, D. Then I also have a lateral face over here, right? Right here is a lateral face. It's a triangle as well. I'm going to name it N, O, D. Triangle M, or N, pardon me, N, O, D. Now, here's one thing that should be helpful. There's more lateral faces than just two. Okay, because there was a lateral face that came off of this edge and went up to the vertex. There's a lateral face that went off of the edge NO and went to the vertex. So since there are four sides to this base, there will be four lateral edges as well. Okay, so our next one, let's see, L or MLD, that is a lateral edge. It's also a triangle, triangle MLD, and it's congruent to the others, right? It's congruent to triangle MND and triangle NOD. It's just drawn, again, to appear three-dimensional. And so it looks like it's not. And then we also have triangle LOD, right? That would be a lateral face, triangle LOD. All right, so again, if your base has four edges, then you're going to have four lateral faces. If your base has five edges, you're going to have five lateral faces. Okay, they all connect. All right, then let's look at D. We want to know the lateral edges. So I'm going to erase this. Remember, the lateral edges connect lateral faces. Okay, so we have lateral edge MD. So that's a segment. So it's going to be segment MD. And we have one N to D. Okay, so segment ND. Because again, it's connecting two lateral faces. OD and LD. Segment LD is another lateral edge. Okay, again, lateral edges are the edges between two lateral faces. All right, let's look at the definition of a polyhedron. A polyhedron is a closed surface of polygonal regions. So each polygonal region forming the surface is a face. So it's a closed surface of polygonal regions. Okay, so a polyhedron is, you can put a couple polygons together even. All right, again, it separates space into three disjoint sets. We should know this by now. We have the polyhedron itself, the interior, and the exterior. So we're seeing the same thing with dots, or with points, with lines, with circles, with any shape at all. Okay, we're getting three disjoint sets. Let me clear this. So and it's named by the number of faces. So it's named by the number of faces that it has. Faces, not edges, not vertices, nothing else. We care about the number of faces. All right, so let me clear this so we can move up to the example. All right, so example 2. Notice we do have this table over here to help you classify polyhedra. Just like on the last one, we had help classifying polygons. So example 2 says classify each figure as a polyhedron. Then classify any cones or cylinders as specifically as possible. So anything that's a cone or a cylinder, we want to classify more specifically. So let's look at A. In order to classify it, we need to know the number of faces that it has. Okay, so if we look at this one, the base is down here. So I'm going to kind of shade the base for us. Hopefully that'll help you kind of see it. So we have a base, that's a triangle, and so then we should have 3 more faces, right? We have the face that comes up here in the front, the base that comes here kind of to the left, and then we have the back triangle, that face that's going to come all the way through there. So this has 4 faces. Okay, because the base that we looked here is considered a face as well. So 4 faces equals a tetrahedron. Now, I need to think about, is this a cone or a cylinder? What do you think? Yeah, it is. It's a cone, or, sorry. Yes, sorry, it's a... Classify any cones or cylinders as specifically as possible. It's a pyramid, and a pyramid is a cone. Yes, okay, sorry, I had to think about it for a second. Okay, so how specific can we be? Well, let's think. Remember, it has a base that's the shape of a triangle, and it comes to a vertex. So that makes it a triangular and it comes to a vertex, so that makes it a pyramid. So it's a tetrahedron or also a triangular pyramid. Because remember that cone, the definition of a cone is just any, like the union of the region, okay, and all of its segments with a boundary, but it comes to a vertex. All right, so let's look at B. Okay, so B, we have this like square in the middle, or rectangle, I guess I should say, and it comes to a point, a vertex on the top and the bottom. So is that a cone? No. Is it a cylinder? No. These look like they're parallel, but a cylinder has parallel bases, not parallel vertices. So it's not that. So we're just going to name it. So we need to count the number of faces. Okay, so this is not a face, right? That's just like if we cut through it, that would be a cross section, but it's not a face. Okay, so, but we do know that it has 4 sides there in the middle, which means it's going to have 4 faces down here, right? So we have 1, 2, 3, and then there's 4 in the back, which means it's going to have 4 faces up here as well. Okay, so 4 plus 4 makes 8 faces, and 8 faces is an octahedron. Okay, if we look at 6, okay, we can see our base here is a rectangle of some sort, okay, and we also have a base on the top that matches, right? Those are the same. So if I have 2 bases that are parallel, that does make this a cylinder. Okay, so that's we're gonna have to deal with that in a minute. So currently though, how many sides does a cylinder have? Or faces, pardon me. So it's got a bottom and a top, so that's 2. Then it has a front, a right, a back, and a left. So that's how many? 6. So 6 is a hexahedron. So hexahedron. And we're going to name it as specific as possible. So the base is a quadrilateral, and it's a cylinder or a prism. So we're going to call it a quadrilateral. That should be an A in there, L. Quadrilateral prism. We could probably, it kind of looks like a right prism, but we can't assume that. So I'm not going to put it's a quadrilateral right prism. We're just going to put quadrilateral prism. Okay, D. If we look at D, it has a base that's 5 sides and a vertex. So does that classify it as a cone or a cylinder? Yes. Okay, so this is a type of cone because it comes to a vertex. So let's go ahead and name that as specific as we can, and then we'll name it as a polyhedron. Okay, so if we have a 5-sided shape on the bottom, that's a pentagon, right? So this would be a pentagonal. So it's like pentagon, AL, pentagonal, and then we would call it a pyramid. Pentagonal pyramid because it comes to a vertex. So it's a cone that we call a pentagonal pyramid, and then how would we name it as a polyhedron? So that's when we look at the number of sides, or the number of faces. Goodness, sides and faces are pretty close. They can be the same thing and be interchangeable. All right, but if I have this one face down here, and it has 5 sides to that face, that means there's going to be 5 faces coming off of it. So let's see. If you think about this as a net, right, there's going to be this triangle and this triangle and this triangle. That one looks really terrible, actually. And that triangle, and one more. Like if I would open that up and squash it down, right, it would open up like this, and we could very easily see that there's the one face on the bottom, and because that face has 5 sides, there's 5 more lateral faces. So there's a base and 5 faces, which means 6 faces. So again, we have a hexahedron again here. Okay, this last one. Is it a cone or a cylinder? Hopefully you're like, no, it's not. Okay, so very good. Now, the tricky part here is counting this up and seeing how many sides it has, or how many faces. Pardon me. Man, I'm really struggling with sides and faces today. Hopefully you do better than I do. How many faces it has. So if we kind of look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here that we can see, okay, which means there should be 10 in the back, which would make this have 20 faces, okay, which would make it the icosahedron. Okay, so it's an icosahedron. Such a fun name. Such a fun name. All right. The last thing, then, let me clean this up and we'll move down to that last little bit. So hopefully you got all that stuff in there and got the mouthful there of icosahedron. All right, so the last thing is regular polyhedron. So remember, a regular polygon, okay, was one that had angles and sides that were equal. A regular polyhedron is a convex polyhedron whose faces are all identical, regular polygon regionals, with the same number of edges meeting at each vertex. So again, all the faces are identical, regular polygonal regions is the key there. Okay, so we have a regular tetrahedron, which means each of those faces is equal. Okay, regular is equal. They're all identical. A regular hexahedron. This is a cube. Okay, because every single face is identical. A regular octahedron. If you ever play with magnetiles, right, you can get this regular hexahedron, a regular tetrahedron, a regular octahedron with those magnetiles. Okay, you could build all of these because they're all identical faces. So regular octahedron, a regular dodecahedron. Okay, so that's 12 sides. Do is 2, like dos in Spanish. Deca means 10. So 2 plus 10 is 12. So that's 12 sides. And a regular icosahedron, which is that 20 sides. Okay, wonderful. Those are regular polyhedrons. All right, all that's left there is for your on your own, and I will see you tomorrow.